Welcome back to Quite Basic Math. Now we'll be talking about a concept in mathematics that we regard as complex numbers. You might have been familiar with real numbers, but now this is a different space of numbers that we call complex numbers. Now the complex numbers have a root. What I mean by root is they have a unit, they have a basis for their formation or for their existence. Now, our real numbers can take care of numbers that we can capture on our real number line. Remember your real number line, 0, that separates the negative side from the positive side. And every number you can capture on your real number line, right, is not a complex number. I take it again. Every number that you can't capture on your real number line is a complex number, or complex numbers are numbers that can't be captured on your real number line. Alright, so now the first basis of that number, or the unit of this number, is what we call I. Now you must have solved questions before where you are taking the square root of a negative number. Let's say square root of -5, square root of -1, square root of a negative number, -20. There is a problem. Before now, probably in secondary school, you must have learned that you say something like it's impossible, or you say something like it cannot be solved, or math error, as the case may be. A calculator will tell you math error or syntax error. I think it should be math error if it's a situation where the calculator has not been set to complex mode. If it's on MTH mode, math mode, it's going to just tell you math error. But if you're on complex mode, then it's taking you to the complex domain. Now in the complex domain, we are now having a set of numbers. We are looking at how to deal with numbers that involves a negative square root. Okay, so the basis for them is I, square root of -1. So every other form of complex number can revolve or evolve around this. I equals to the square root of -1, and this implies that I squared is -1. How did I come by this? If you square both sides, if I say I equals to square root of -1, and if I square both sides, it means that I squared is -1. Alright, now this is what would form the basis of complex numbers. So every time I put down I, you should understand that I mean the square root of -1. Now let's start. Now we're going to have a generic Z. Let Z represent every complex number or any arbitrary complex number, and then let's say Z equals to X plus IY. Now take note of this very well, because we'll be making reference to this Z. Now Z is representing the set of complex numbers, or an arbitrary complex number that has a real part and an imaginary part. Now this part that has the I, that has the actual square root of -1, this I here, right, is what we call the imaginary part of the complex number, and this is the real part. So every complex number actually has can be split into the real part and the imaginary part. So let me do some notations for you. So if I write RE of Z, what I'm saying is the real part of Z. In this case, where Z is X plus IY, the real part of Z is X, and in this case, where Z equals to X plus IY, the imaginary part, which is denoted as IMZ of Z, is equals to Y. Okay, so in case you find questions where you are asked to evaluate RE of Z, they are just asking you for the real part of Z, that is the part of the complex number that does not include an I, while the imaginary part is telling you that, okay, give me the coefficient of the part that is being multiplied, of the part that includes I. Alright, I believe you understand that. Okay, now let's press further. Now we have said that a complex number can be written as Z equals to X plus IY. Now let's look at some basic properties of the complex number Z. Now your complex number Z also has something called conjugate. Complex number Z has something called conjugate, and it is written as Z bar. Okay, so Z bar is simply saying that is the complex conjugate. Okay, it's your complex conjugate. So the conjugate of your complex number, so far as this course is concerned, or this video is concerned, and even in many texts, you would see your complex conjugate written as Z bar. and is actually equals to x minus iy. So the way we find our complex conjugate is locate the place where you have your imaginary part and then negate the sign. Okay, so if it is a plus, if it's plus, of course, if it's plus you have, it becomes minus, and if it's minus you have, it becomes plus. Okay, so that's your complex conjugate. All right, now I want you to take note of this property, this very important property. Now if I multiply z by z bar, I will get something, but for now let's hold on, we'll come back to it very soon, so you can see the importance of what I'm about to draw from there. Now let's go on. In our complex number, we can do different things to our complex number, just like in real numbers. What I mean by real numbers, the numbers that you can find on your real number line. For example, 2 is a real number, right? 2 is a real number, and you can add real numbers, is that not so? You can add them, it gives us 5. You can multiply real numbers, it gives 6. 2 times 3. You can divide real numbers, 2 over 3. You can do different algebra on real numbers. So we can also do the same for complex numbers. So let's start with addition and subtraction. Now you can add two. Let's assume we have two complex numbers, z1 which equals to x1 plus iy1, and we have another complex number, z2 which equals to x2 plus iy2. Now you can add up these complex numbers and you can also subtract them. All right, so let me do this. If I add the complex numbers z1 and z2, okay, I will have something like this: x1 plus y1, right, plus x2 plus iy2. Now if I evaluate this will give me x1 plus x2 plus iy1 plus iy2. Now the important part of doing this is for you to see that when you are asked to add two complex numbers, or when you are adding up two complex numbers, the real part add up and then the imaginary part add up. Now this implies that the addition of your complex numbers z1 and z2, okay, will be equals to the addition of the real parts plus the addition of the imaginary parts. Okay, so this would be complex number. Again, I want you to familiarize yourself with this notation. So real part of z1 plus z2 equals to x1 plus x2, all right, and the imaginary part of z1 plus z2 actually is equals to y1 plus y2. I believe you can already tell what the subtraction of two complex numbers will give. It follows the same suit. Okay, so if I have two complex numbers subtracting each other, let's say this, let's use the complex number we have already stated, z1 and z2. Now if you have x1 plus iy1 and then you have minus x2 plus iy2, this is what you have. You have x1 plus iy1, right, minus x2 minus iy2, and then if this implies that your z1 minus z2 will be equals to x1 minus x2, right, plus you factorize i into y1 minus y2. So you can see that just like how you subtract, just like we have in addition, when you have two complex numbers that are subtracting, you subtract in the real part and as well the imaginary part. Okay, the same goes if I'm going to write the real part and the imaginary part. You know the drill already. Now you can also multiply two complex numbers. Let's use our z1 z2. You can multiply complex numbers, say z1 and z2. So how do we multiply complex numbers? So you do it like you're expanding, just the way you expand binomial factors, right? So x2 plus iy2. Now if you multiply this will give us, the way you multiply this times this, this times this, this times this, and this times this. So you have x1 x2, right, plus I x1 y2 plus I x2 y1 plus I squared y1 y2. Do not forget what I said about I squared. we said that that I is the square root of -1, which means that I squared is -1. So do not forget that. Okay, so what do we then have? This implies that our z1, z2 is actually equals to x1, x2, right, plus I x1, y2 plus I x2, y1. Then I squared is -1, so that's just negative y1, y2, okay? And then your z1, z2 now will be equals to x1, x2 minus y1, y2. You can factorize I here. Then you have x1, y2 plus x2, y1. So this is the multiplication of two complex numbers, okay, z1 and z2. Let's do what we did the other time. So the real part of the product of z1 and z2 will be x1, x2 minus y1, y2, and the imaginary part of the product of two complex numbers z1 and z2 would be x1, y2 plus x2, y1. Now please take note of all of these things because they have a way of playing out whenever you are given questions that are not necessarily involving numbers, but they are involving just letters. So you should be able to know how to go about every one of these ideas. Okay, finally, you can also divide two complex numbers, say z1 over z2. What you do here is simply what you do when solving sorts. If you remember sorts, if you have two sorts that are dividing each other, you can do something we call rationalize. So this is the same thing here. You rationalize this fraction. So how do you rationalize this? You multiply the numerator and the denominator by the conjugate of the denominator. Come again. You multiply the numerator and the denominator by the conjugate of the denominator. So you have x1 plus iy1 over x2 plus iy2. The conjugate of the denominator is x2 minus iy2. So you do the same. Now, when you do this to a fraction, you are not changing the fraction. So at any point in time when you rationalize, you're actually not altering it. You are not altering it, you're just simplifying it. Because this divided by this is 1. So if you multiply anything by 1, you're actually going to get that same thing, meaning you are not actually altering the fraction, you're only simplifying the fraction. Now let's expand this. This will be x1 plus iy1 multiplying x2 minus iy2, okay? Then divided by x2 plus iy2 multiplied by x2 minus iy2, okay? So let's simplify this further. This is going to give us z1 over z2 will be equals to if you expand this, that will be x1 x2 minus I x1 y2 plus I y1 x2 minus I squared y1 y2, okay, divided by, okay, x2 squared minus I x2 y2. Now pay attention to this denominator because every time they will play out like this. You have your inner product. I mean, you have this guy here. This guy will always be 0. Always be 0 whenever you rationalize. So take note of that. Plus I squared y2 squared, okay? Now this will be equals to, your numerator now would be x1 x2 minus I x1 y2 plus I y1 x2. Now I squared, don't forget, is minus 1, and you have a negative here, so minus 1 times minus 1 times minus, basically, which is plus 1. That's just plus y1 y2, okay, over x2 squared. Then I squared here, I squared, there's sorry, I omitted something. Sorry, that's a mistake. If you multiply this by this, you should have minus I squared, not plus I squared. This is minus, sorry about that, minus, okay, so that by the time you, I squared is minus 1, then minus here, that will be plus y2 squared. So this is what you will always get in your denominator, okay? I mean, you would always have, whenever you want to rationalize something like this, you would always have this squared plus what this is, guys, whatever this is squared. Okay, so your z1, simplifying further, z1 over z2 now will be equals to x1 x2, okay, plus y1 y2 minus, or you can say plus I into y1 x2 minus x1 y2. Okay, so what I basically did was to factorize I from here, plus I factorized plus I. That's why we have it flipped, over x2 squared plus y2 squared. Now I can break this fraction such that I have x1 x2 plus y1 y2, okay, over the denominator. I'm doing this so that I can evidently show you that whatever complex number you are given, you can always break it down to the real part and the imaginary part. So you evidently see the real part and the imaginary part. Okay, that's why I'm doing this. So if you have been asked now for a question like this, now I can write that the real part of the division between z1 and z2 will be equals to x1 x2 plus y1 y2, okay, over x2 squared plus y2 squared, okay, and the imaginary part of z1 over z2, okay, is actually equals to y1 x2 minus x1 y2 over x2 squared plus y2 squared. All right, I hope things are not getting too intense here. What I've done so far is just all the algebra of complex numbers. Okay, we have been able to see how complex numbers can be added, complex numbers can be subtracted, complex numbers can be multiplied, complex numbers can be divided. So this forms the basis of the algebra of complex numbers. This forms the basis of the algebra of complex numbers. All right, in the next video would look at how the complex number can be expressed. We'll look at different forms in which the complex number can be expressed to better understand how complex numbers can be solved and how they can be understood in their full-fledged domain. I hope you learned something, and please do well to like, subscribe if you haven't done so, and leave a comment if you like me to know something, if you like to ask questions to gain more clarity, or if you like to acknowledge that you've gained clarity in the video you've just watched. Thank you.